Okay, this video is a rundown of 7C in case you've finished 7B. This is basically what we've been working towards in this whole chapter. The first thing that we need to learn about is a thing called the remainder theorem. The remainder theorem is going to be really useful to us. If you notice here, we've got a cubic divided by a linear, and the remainder was 25. Now, x take 2, although it's not a perfect factor of this cubic, because obviously there's a remainder, so it doesn't actually divide perfectly. If this was a factor, as a solution, it would be x equals 2. And if we substitute that in to the cubic, okay, so wherever there's an x here, I'll substitute in 2, I get an answer of 25. Okay, so that's pretty cool. Because what we know is that if we were substituting something in and we got an answer of 0, that would then be a solution of that cubic. So, skipping all a bit of that jargon, in question 1, all you are going to do is practice that process. That if you have x take 1, if you substitute in 1, wherever there is an x here, you will get the remainder of what it would be to divide by x take 1. Okay, if you are having to substitute in this one, 2x plus 3, you might have to write 2x plus 3 equals 0. So it'll be 2x equals negative 3, x equals negative 3 on 2. So you need to work it out as if it was like when we work out the answers to the solution of a quadratic. You substitute that in wherever there is an x, and you will get the remainder as if you were dividing by 2x plus 3. Seems sort of pointless, but it is going to be really useful. So question 1 is just practicing that remainder theorem. Question 3, without dividing, show that the first polynomial, so the cubic, is exactly divisible by the second, or also showing that x take 1 is a factor of this cubic. So if we substitute in 1 into here, 1 cubed take 1 squared plus 1 take 1, we end up with 0, which means that it is a factor, okay? So it's that 1 is a solution to that cubic. And so visually I can show this a bit better for C. So if I actually put this equation into Desmos, and I'll need to move that, so I've just put that equation in there. Okay, so that's what that graph looks like. The question is x plus 2 exactly, is this exactly divisible by x plus 2, or is x plus 2 a factor? And if we have a look at the graph, we can see that the solutions to this cubic are negative 2, 0.5, and 3. And this negative 2, that is what x plus 2 is as a solution. Because when x plus 2 equals 0, then x equals negative 2. So x plus 2 is the factor, and x equals negative 2 is a solution. So when we have a remainder of 0, that we have sort of proven that this linear equation is a factor of that cubic. So for 4, all you have to do is substitute in x, when for this one it would be a positive 3, for this one it's a negative 3, and then make the equation equal 0 to figure out what m is. So this is all leading towards one big concept, how to factorize a cubic. And we're going to go to example 12 to do this, so we don't give away too many answers. Okay, so we've got a cubic here, and I'm just going to get away from that for now. This is, let's say that's that cubic here. We know that the whole point is that we want to break this up into a linear and a quadratic. That's our first step, okay? And so we want to work out this linear part. And there is going to be a bit of trial and error involved, which seems a bit crazy. If we could trial and error some numbers in for x here, like a 1, a 3, a 5, and if they equaled 0, we know that that would be a solution. So if I trialed the number when x is a 4, and I put it into this part of the cubic, and it equaled 0, I would know that that is a solution, because that would mean that it is a solution along the x-axis. And that would mean that the factor would be x take 4, okay? Now you're probably thinking, hang on, there's like a lot of numbers, there's like 5, 7, a lot of numbers in the world. So how are we going to just guess some of them? Well, there is a bit of a trick to which numbers you guess. If you have a think about this linear part and this quadratic part, if I expanded this side of the equation, and I'll get something like I did earlier, which is like this, there only ends up being one multiplication that leads you to this constant at the end. What I'm saying is that if I do x times x squared, x times gx, x times f, they're all going to end up with an x in them. If I do negative m times x squared times gx, they're going to have x squareds and x's in them. The only way I get this constant at the end here of this cubic is when I take this part of the linear factor and I multiply it by this part of the quadratic, which means that this part of this linear factor that we are looking for, this mystery number, multiplies by something and it equals this n part to the cubic. That's the only part that makes up that part of the cubic. So when I'm looking at this 6 here at the end here, and I'm trying to think of what possible linear factors or solutions I could try, I know that they have to be able to be a factor of 6. They have to be the factors of 6. That's the ones I'm going to try. So the factors of 6 are 1, 2, 3, and 6, and it could be the positive or negatives of those. Okay, so that's this part over here. And so in the textbook, the first one they chose was 1. And oh, they got it, okay? So something you might not realize here is that this can be done a few times. If 1 hadn't worked, if there was like an answer of negative 4, then 1 wouldn't be a solution. So you might have to try 2, negative 2, 3, negative 6, until you get one that works. Okay, now a lot of the time you get lucky because there are actually 3 factors to this cubic. So, you might not all get the same one. You might get a different one. But as soon as you get one that works, you go, okay, so if 1 is a solution, then x take 1 is a factor of this cubic. Okay, hurrah, we've already got one. Now we need to work out the quadratic part of this cubic. So we need to use long division to divide. So we take the cubic and we divide by x take 1. Of course, there is a remainder of 0. If you get a remainder at this stage, you've stuffed up, because if it's a factor of this cubic, there should be no remainder. And you'll end up with a quadratic at the top. So we know x take 1 multiplied by x squared take x take 6 equals this cubic. Okay, dun, dun. And then we can just easily factorize that cubic by 2 numbers that multiply to equal negative 6 and add to equal negative 1, just like when we're usually doing a quadratic. Now you'll notice that these were the 3 factors of this cubic. So someone sitting next to you might have done this in a different way. They might have decided first to substitute in here negative 2, which is also a solution to this cubic. And they would have substituted that in and it would have equaled 0. And then they would have said x plus 2 is a factor. And they would have divided by that factor and got a different quadratic. And when they solved that quadratic, they would have got answers of negative 1 and negative 3. So hopefully that makes a bit of sense of how you solve a cubic. Go back to my key learning points. You basically have to do some trial and error to find one of the solutions. But you look at the factors of the constant to narrow this down. So you look at that end number of the cubic. The factors of that give you some ideas of things to trial and error. You substitute in these numbers into the cubic until 1 equals 0. When you find a solution that works, you turn it into a factor. So if the solution you tried was when x was a 3, the factor is x take 3. Then you do the long division using this factor to find the quadratic part of it. You only ever do long division once, okay? I know some people don't listen properly and I see their work and they end up doing long division like 10 times until they've found one of the factors. And that's the whole point of the remainder theorem, is that we can simply test them until we get a remainder of 0 and then we know it's a factor and then we'll do the long division. We don't want to do long division like 4 times only to, okay, yay, this one has a remainder of 0, it's a factor. No, we only have to do the long division once after we've worked out that it is definitely already a factor by using this simple substitution method. and then you get the quadratic and you factorize the quadratic part. Cool, I think I might leave that there. Don't worry about this whole rational root theorem for now. You can have a read of it if you want to, but not necessary. And then the only last question that I'm not going to do in this video yet is factorizing these ones, and you can read example 15 for those or just have a go at them. Cool, thanks for listening. Bye bye.